Welcome to the lecture series on CFD, Part 2. This is lecture 26 on discretization methods for moving grids. This lecture starts with an introduction to the effects of moving boundaries on fluid flow. We distinguish between motion of wall boundaries in tangential and wall normal direction. If walls are oscillating with a small amplitude, the wall motion can be accounted for without moving the grid. The modeling of small amplitude wall motion will be described and demonstrated in an example. If wall boundaries move over a larger distance, the grid has to move and adapt to the new position of boundaries at each time step. The change of cell size and position can be accounted for in different ways. We describe how equations written for fixed control volumes can be used even when the grid is moving. The most widely used approach is to use equations written for moving control volumes. This allows simulation of flows in solution domains with an arbitrary grid motion. An important ingredient in methods based on equations written for moving control volumes is the so-called space conservation law. We explain how this law can be satisfied and how its implementation in a CFD code can be tested. Finally, 3 examples of simulation of flows with moving boundaries are presented. Simulation of flow around a sphere oscillating in x direction with high frequency and small amplitude. Simulation of laminar piston-driven flow using 2 approaches. And simulation of flow in a mixer using sliding grids. In many practical applications, walls bounding fluid flow are moving. Examples are flows in rotating machinery, mixing devices, around floating or flying bodies, or around deforming bodies. When a wall is moving only in tangential direction, it is enough to specify wall velocity as the Dirichlet boundary condition. The grid does not have to move. Examples are couette flow, translation of one channel wall parallel to another fixed wall, and flow around a rotating cylinder. If a wall is moving in the direction normal to it, it is displacing, that is pushing away, the fluid when it moves inwards, or sucking, that is pulling towards wall, the fluid when it moves outwards. These effects must be either modeled via source terms or accounted for by moving the grid with the wall. The modeling of wall motion effects with source terms is only applicable when the amplitude of wall motion in the normal direction is small. Otherwise, modeling errors can become large. Let us have a look at an example of flow with a tangential wall motion, a laminar flow around a rotating cylinder at a Reynolds number based on undisturbed flow velocity and cylinder diameter of 500. This figure shows velocity vectors around a circular cylinder rotating counterclockwise. In the upper zone, the cylinder wall is moving in a direction opposite to flow direction. This leads to deceleration of fluid in the vicinity of cylinder. At cylinder wall, the no-slip condition requires that fluid particles move with wall velocity. In the lower zone, the cylinder wall moves in the same direction as the external flow, which leads to acceleration of fluid in the vicinity of cylinder. In the animation of pressure variation, we see that pressure is low where the cylinder wall accelerates the surrounding fluid, while it is high where the fluid is decelerated. This results in a non-zero lift force, that is, the force in the direction perpendicular to the flow direction. This is called the Magnus effect. This diagram shows the variation of drag and lift force on cylinder when it is initially held fixed and then suddenly started to rotate with 2 revolutions per second. While the cylinder is fixed, the lift force oscillates around 0 due to vortex shedding, while the drag force is almost steady. Once the effects of cylinder rotation are settled, the drag force drops almost to 0, while the lift coefficient increases to almost 10 and becomes nearly steady. As the animation of pressure variation shows, the flow is almost steady without vortex shedding. The Magnus effect is used in engineering to generate lift for small aircraft or to move ships in wind using flattener rotors instead of sails. Already in 1924, more than 100 years ago, ships with flattener rotors were built. Rotating cylinders generate more lift than sails at the same wind speed, but one needs an energy source to rotate the cylinders. Propellers are more efficient and flexible, and thus they displaced flattener rotors while the energy needed for propeller rotation was cheap. These days, more and more ships are again equipped with flattener rotors to allow energy saving when wind conditions are favorable. This picture shows a ship with 4 flattener rotors built in 2010. North end plates on flattener rotors installed to avoid tip vortex formation, which has a negative effect on the lift. In some engineering applications, walls move in an oscillatory manner at high frequency but small amplitude. An example is the vibration of cooling water channels in internal combustion engines. In this case, the analysis can be performed using a fixed grid and the equations written for fixed control volumes. Here, the conservation equations for mass, momentum, and scalar variables are shown. Note that the time derivative is evaluated at the fixed location in space, that is, it represents the local time derivative. If a wall moves in the normal direction, one can account for the displacement or suction of fluid by introducing appropriate mass source terms in the continuity equation. When a wall moves inwards and displaces fluid, this is equivalent to having a fixed wall but injecting the same amount of fluid that the wall would have displaced by its motion. Accordingly, when a wall moves outwards, it sucks fluids behind it, which can be accounted for with a fixed wall and a mass sink, which sucks the same amount of fluid that would follow the wall during its motion. Both cases can be described by a source term in the mass conservation equation in cells attached to the moving wall as follows. The mass source of sink is equal to the product of density, velocity component orthogonal to wall, and wall area, which is equivalent to a convection flux through the inlet or outlet boundary, depending on flow direction. Thus, to simulate flows involving small amplitude wall motions, we can use a fixed grid and implement mass source terms into the continuity equation, that is, the pressure correction equation, in control volumes next to moving walls according to the above expression. If the wall motion is irregular, the flow is unsteady from any viewpoint, and in this case one cannot simplify the problem. The grid needs to follow the wall motion and adapt to its new position and possibly change shape in each time step. There are several options for numerical simulations of such flows, both with respect to the equations and to the grid used. One option is to move the grid with the body but use equations for fixed control volumes and account for grid motion by evaluating the local time derivative at cell centers using interpolated solutions from the previous time step to the new grid position. The same approach is used when regridding is performed. For example, to compute the local time derivative at the new cell center location when using the quadratic backward scheme with 3 time levels, this expression is used. The solutions from time levels n-1 and n-2, which were computed for cell centers at previous locations, need now to be interpolated to the new cell center location as indicated in this figure. Solid lines show the control volume at the new time level n, while dashed lines show control volume at the previous time level n-1. The new and the previous cell centers are indicated by the corresponding superscripts. The approach described in the previous slide is possible if a fully implicit time integration method is used, because then the fluxes and source terms are computed only at the latest time level. The solutions from previous time steps appear only in the time derivative and can be computed as described in slide 9. In addition to interpolation needed to compute the rate of change term, one also needs to account for wall motion in control volumes next to walls. The method described in slide 8 can be used. interpolation of old solutions to the new cell center introduces additional discretization errors. An example of second order is given by this expression. The value of the previous solution at the new cell center position is computed by adding to the solution at the center of the control volume at its previous position the product of the gradient computed at the old position times the displacement vector from the old to the new cell center location. If the grid does not move more than half a cell per time step, the error from this interpolation will be of the same order as errors in convection fluxes, which require interpolation between two cell centers at the same time level to the common phase center. However, in case of large grid motions, the errors can become significantly larger. Interpolation errors can be reduced by using higher order approximations. The largest problem with this approach is the motion of walls in the direction normal to boundary, because here usually very thin prismatic cells are used to account for high gradients in boundary layers. It can happen that cell centers at the new time step fall outside solution domain from previous time step, and thus no old solution is available for interpolation, as indicated in this sketch. At time step n+1, the near wall cell center is outside the solution domain from the previous time level n. One can still use the interpolation expression from slide 11, but the errors are likely to be large. For more details about this approach, see PhD thesis of Hidayat Hadjic from the Technical University of Hamburg, which you can download from this link. The other option is to use equations for moving control volumes. Then no interpolation of old solution is needed. The fact that solutions from different time steps are associated with different spatial locations are taken into account within the rate of change and convection terms. Still another possibility are immerse boundary methods, which were described in slides 11 to 13 of lecture 21. When equations written for moving control volumes are used, in addition to conservation equations for mass, momentum, and scalar quantities, the so-called space conservation law needs also to be accounted for. Note that the time derivative in these equations expresses the change in time along the path of the cell center motion, that is, for different locations at consecutive time steps. Although these terms are discretized in the same way as time derivatives in equations for fixed control volumes given in slide 7, the meaning is different. Another difference compared to equations from slide 7 is apparent in convection terms. They are now computed with the relative velocity, that is, fluid velocity minus velocity of the control volume surface. If the control volume moves exactly with fluid velocity, then the time derivatives in equations from previous slide become material derivatives, and convection terms become zero. In this case, control volumes are identical with control mass, that is, the same fluid remains in the control volume. The space conservation law is not solved as a transport equation, but volume fluxes through cell faces due to control volume motion and cell volumes need to be computed so that it is satisfied. Why is this important becomes obvious when considering the continuity equation for a constant density flow, in which case density drops out of the equation. The first two terms in the continuity equation represent the space conservation law, and the third term requires that the velocity field is divergence-free. Thus, in an incompressible flow, the continuity equation must reduce to one of the following expression whether the grid moves or not. This means that the space conservation law must be satisfied in discretized equations to ensure a divergence-free velocity field and mass conservation. If grid velocities are not consistent with space conservation law, artificial mass sources result. Let us now see how the discretized space conservation law can be identically satisfied. We use the quadratic backward time integration scheme with 3 time levels, but the same approach is valid for Crank-Nicolson and other schemes. The discretized form of the space conservation law for the chosen discretization scheme is given by this expression. On the left-hand side, we have cell volumes at 3 consecutive time steps, and on the right-hand side, volume fluxes due to cell phase motion from the latest time level. It is important to note that the difference in cell volumes at 2 consecutive time steps is equal to the sum of volumes swept by each phase during one time step, as given by this expression. The volumes swept by one cell phase during 2 consecutive time steps are indicated in this figure. The space conservation law can be then expressed as shown in this expression. The index k runs over all phases of a control volume. In this equation, we have sums over all cell phases both on the left-hand side and on the right-hand side. Although this is not the necessary condition to satisfy the equation, we can request that the above expression should be satisfied for each cell phase k. That is, we define the volume flux through the cell phase k at time level n+1 via the volumes swept by that phase during the past 2 time steps, as given by this expression. Here we introduce the shorthand notation for the volume flux through the cell phase, also called grid flux. The space conservation law is then identically satisfied. The volumes swept by each cell phase over one time step, delta V, are computed directly from grid position at 2 consecutive time levels. With this approach, the velocity of the cell phase, Vs, does not need to be explicitly defined. The mass flux through cell phase K at the latest time level n+1 can now be computed as shown by this expression. From the mass flux due to fluid velocity, we subtract the mass flux due to grid motion. The discretized mass conservation equation for one control volume is then given by this expression. The discretized mass conservation equation for one control volume is then given by this expression, containing an approximation of the time derivative using volumes and densities from 3 time levels and mass fluxes through control volume phases from the latest time level. If grid motion is not prescribed but is part of the solution, for example in the case of flying or floating bodies, the new volumes are updated during outer iterations within each time step. This will be further addressed in lecture 36. The convection fluxes are zero and no source terms are needed in the continuity equation at wall attached cells when the analysis is performed using moving control volumes. Fluid displacement by moving walls is taken into account through the contribution of control volume motion to convection fluxes. Large time steps can be taken, but temporal discretization errors will be large if cell phases move too far within one time step. A good test of moving grid implementation in a CFT code is: take a closed solution domain with no inlets or outlets and with fixed boundaries. Set fluid velocity to 0 in all cells at the initial condition, and just move the interior grid in each time step, for example in an oscillatory manner. If the space conservation law is properly implemented, fluid will remain at rest. Otherwise, artificial mass sources or sinks will result and cause the fluid to move. If that happens, there is an error in implementation. Let us further discuss the methods presented so far using suitable test cases. The first test case is the flow around a sphere whose diameter is 61.4 millimeters, oscillating sinusoidally in x direction with an amplitude of 5 micrometers and a frequency of 6 kHz. The fluid is water and constant fluid properties are assumed. 2 simulations are performed, with a moving grid performing rigid body motion with sphere, and with a fixed grid and source terms in cells next to sphere wall as given in slide 8. Only a quarter of the flow domain is considered with 2 symmetry planes, z equals 0 and y equals 0. The plot shows the polyhedral grid near sphere in one symmetry plane. The thickness of the first prism layer next to sphere wall was 0.225 millimeters. The amplitude of oscillation was 5 micrometers, which is only 1/45 of the first prism layer thickness. The cells next to sphere wall, which received the source term described in slide 8 in the case of a fixed grid, were identified by radius smaller than 30.925 millimeters. These figures show the comparison of pressure and x component of velocity at one instant in time predicted using two approaches: moving grid on the left and fixed grid on the right. While there are small differences in maximum and minimum values of contour levels, the results look practically the same. These plots show the quantitative comparison of results obtained using fixed and moving grids. Shown are the force on sphere and the minimum velocity in the direction of motion and the maximum and minimum pressure in the solution domain. All quantities oscillate periodically due to sinusoidal variation of motion. These vertical red lines resulted from disturbances caused by stopping and saving the simulation using moving grids at one time and restarting it later. The results from two simulations presented in slides 19 and 20 look very similar. Simulation with a fixed grid and a mass source term shows a small disturbance in pressure each time the velocity of sphere motion was zero, that is, when changing the direction of oscillatory motion. It is at the moment not clear why this happens. The maximum and the minimum pressure at t equal 0.003752 seconds, see slide 19, differ. Maximum values by just under 1% and minimum values by circa 2.7%. Larger differences are only visible in the minimum velocity within the solution domain. It appears to be getting lower with each period when a fixed grid with a mass source is used. These differences are relatively small and could be tolerated in some engineering applications. The second test case is the simulation of intake and exhaust strokes in a simplified piston cylinder assembly using Cartesian grids and two-dimensional axisymmetric solution domain. The grid in the intake pipe is fixed, while the grid in the cylinder moves according to piston motion. In one simulation, equations written for moving control volumes involving the space conservation law are used and the grid topology is not changing. In another simulation, equations written for fixed control volumes are used and solutions from previous time steps are interpolated to centroids of control volumes at the new time level so that the local time derivative can be computed. In both cases, fully implicit time integration methods, implicit Euler or quadratic backward, are used. This approach allows re-gridding, and in one test case, grid in cylinder is replaced several times during each stroke with less cells in axial direction near bottom dead center and more cells near top dead center. More details can be found in PhD thesis of Hidayat Hadžić, see link in slide 11. Plots on the left show velocity vectors at 4 instants during intake stroke. As the fluid is sucked through the intake pipe, a large vortex is generated. During exhaust stroke, as shown in figures on the right, this vortex is squeezed into the intake pipe and pushed out of cylinder. This slide shows instantaneous pressure distribution in the piston cylinder assembly at times corresponding to velocity vectors in slide 22. A low pressure zone is created at the corner of sudden expansion, indicating buildup of a ring vortex around a round jet. This vortex is moving toward piston and the low pressure zone disappears when the piston reaches the top dead center. During the exhaust stroke, a low pressure zone is created as the fluid enters the exhaust pipe near the corner of sudden contraction. This low pressure zone grows with time until, at the bottom dead center, the cylinder stops moving and the inertia of fluid causes a low pressure inside the whole cylinder. These two plots show the comparison of radial profiles of axial velocity at 2 instants, one within intake and one within exhaust stroke, computed using the two approaches. SCL denotes the approach in which the space conservation law is applied and equations for moving control volumes are solved. LTD denotes the local time derivative approach in which equations for fixed control volumes are solved and all solutions are interpolated to the new cell center location. Results from both approaches are practically the same. There are no obvious advantages of one approach over the other in this test case. However, LTD approach is attractive for simulations in which the grid needs to be regenerated from time to time, as the grid quality may deteriorate considerably when the same grid topology is kept all the time during motion of bodies relative to each other. The third test case is the simulation of flow in a mixer using sliding grids. Mixer geometry is shown in this figure. There are 4 axial baffles attached to the cylindrical vessel wall, while the impeller consists of 4 blades inclined by 30 degrees with respect to axis and attached to the central shaft. The outer vessel diameter is 100 mm and the vessel height is also 100 mm. Fluid density is 1000 kg per cubic meter and its dynamic viscosity is 0.1 pascal second. Impeller rotation speed is 60 rpm or 1 revolution per second. The second order quadratic backward discretization in time is used with a time step of 0.002 seconds, that is, with 500 time steps per rotation period. The solution domain is split into 2 regions. One is attached to the impeller and rotating with it, while the other region is attached to the vessel wall and is fixed. This plot shows an axial section through the polyhedral grid. The section plane is passing through the fixed baffles. One prism layer is created on each side of the sliding interface between the 2 regions. This plot shows the grid in a cross section through the impeller, with a zoom into this zone shown in this second plot. Here we see thicker prism layers along sliding interface between rotating and fixed region, whose purpose is to make interpolation across interface more accurate. Along the walls, 5 prism layers are created to capture the boundary layer effects. The flow is assumed to be laminar because the fluid is very viscous and the rotation rate is relatively low. Different arrangements may be required for turbulent flows. This will be addressed in lecture 32. The grid is locally refined near impeller walls because higher gradients are expected there. This slide shows an animation of pressure variation and an instantaneous tangential velocity field in an axial section through the vessel. Impeller blades are pushing fluid downward and sucking it from above as they rotate, thus mixing the flow from zones above and below impeller. The flow is weak near the bottom wall and especially near top wall, which is further away from impeller. Every time an impeller blade approaches the fixed baffle, the pressure ahead of blade increases and behind it decreases. This is even better visible in a horizontal cross-section shown in the next slide. This slide shows an animation of pressure variation and an instantaneous velocity field in a horizontal section through the impeller. Impeller is rotating counterclockwise and its blades are pushing the fluid in front and sucking behind them. This is reflected in the pressure field. We see high pressure on the front and low pressure on the rear side of blades. Every time an impeller blade approaches the fixed baffle, the pressure on the baffle increases. As soon as the blade passes the baffle, the pressure reduces. This plot shows the residual history over several time steps. A fixed number of 5 auto iterations per time step were performed. The under-relaxation factors in the simple algorithm were 0.9 for velocities and 0.5 for pressure. In the last auto iteration of each time step, the normalized residuals are around 0.001 for all variables, which is usually enough in practical applications. This plot shows the comparison of thrust, that is, the force in the direction of rotation axis, generated by the impeller from simulations on 2 grids. Control volumes in grid 1 are 1.5 times larger than in grid 2. Grid 2 is shown in slides 25 and 26. The thrust varies periodically with blade passing frequency. Considering that the range of variation is relatively small, from 0.088 to 0.098, the difference in two solutions is not large. These two plots show the comparison of torque exerted on fixed mixer blades on the left and on impeller blades on the right from simulation on two grids. Control volumes in grid 1 are 1.5 times larger than in grid 2. Grid 2 is shown in slides 25 and 26. Differences in solutions from two grids are not very large in this highly viscous laminar flow. We shall use the same test case later for turbulent flow, where grid dependence will be larger, requiring finer grids. Here is a summary of this lecture. Moving boundaries can be accounted for via mass source terms if the motion is small compared to grid size. This is usually the case when volts are vibrating with high frequency and small amplitude. It is possible to use equations written for fixed control volumes when using fully implicit time integration. One then needs to interpolate solution from one or more previous time steps to the new grid locations. The most general approach is to use equations written for moving control volumes. This allows using large time steps when necessary, for example, to speed up the flow development from an initial to the fully developed state. When moving grids are used, one must ensure that the space conservation law is satisfied. Otherwise, artificial mass sources or sinks are resulting. The space conservation law can be conveniently satisfied by computing geometrically swept volumes between consecutive locations of cell faces. This approach is used in most commercial CFD codes.